Okay, it's Wednesday, September 27th, 2023. Today, we're going to talk about random forest. So you can download the data. It's under week 6, not the data, but the slides. And then we're going to talk about project 1, and we're going to do some pre-processing on the data. It's going to be a working session. About half of today, you can go up, start working on project 1. I'm kind of warning you, if you don't start on project 1 now, you can't do it the night before. Okay, you got to work on it a few nights before, maybe even this weekend. If you're through with the pre-processing, by the end of the weekend, you'll be doing good. Okay. I could have scheduled the project 1 before the break, but I decided to do it after the break to have a little more time. And that's always a hard decision. I don't want you working on your break. You have fun, but give a lot of work. Okay, so that's the plan. A little outlook of where we're going. We will talk about a couple of other machine learning techniques so you have a portfolio of things that you can work with. So I already talked about k-nearest neighbors. We dug into sequential neural nets. Then we're going to talk about random forest. Then something called support vector machines. You have 4 or 5 methods you can use. For project 1, we'll compare one method versus another. Maybe 3 methods. 2 methods is enough. You can actually do convolutional, or not a convolutional, but a sequential neural net, multiple types, and compare that, right? You can add regularization, do all these things, compare the results, put it in a table. Here's what I did. Here's the routine that worked the best. So that's what we're gearing up to. Today, the pre-processing, we'll do the pre-processing working session. There's a whole section in the write-up. Let's do it in an article form, not a report form, but an article. There's a data section. So today, you'll be calling out some data that makes no sense. Just document that in the data section. Right? So that's what we're going to do. Prepare you for writing that section. Okay, so that's the plan for today and moving forward. Turn on the microphone so I can record. I think I was speaking loud enough. Okay. All right. Okay, let's load up some slides and talk about random forest. Okay. Understanding random forest. This is what's called an ensemble learning technique. And we're going to have some new definitions today, some new nomenclature. Let's see, let's hope that we get some slides. Well, that was just so slow. Okay. It's ensemble learning technique, learning approach. And so what ends up happening at the high level, you have these decision trees. And I think of a decision tree as an if statement, but it's more than an if statement because it's a prioritized. It's selected to be the right if statements. We'll get into that. It's a collection of decision trees. Conceptually, you can think of it as if statements. And what we mean by ensemble learning is we're going to have 1, 2, 3 methods, all using decision trees, all in one program. And then at the results are going to be, we're going to use a technique at the end, either called majority voting or just averaging to make the prediction. So random forest kind of automatically does it for you. It's a very simple technique. It's like 2 lines of code. So I didn't want to tell you about that first. It's too easy. The CNNs and do all of those things. It's very simple. I usually start with this technique. It's so simple. And see how good accuracy is. And then try to make my neural net better than that's my kind of approach. So the final prediction is a combination of each of these individual trees, and that's how you make a prediction. Okay. So the pseudocode for this is you do something called bootstrap sampling, and bootstrap is a word that's used and machine learning. And all that is a random sampling of your population sample data. So I have a population of 100,000 observations, and I bootstrap with 1,000. I'd collect 1,000 samples from that 100,000 sample population. Now, why can we do that? Central limit theorem. We're going to talk about that. It's like basically we're going to get our subsample. It gives us a distribution of the whole large population. But we're going to then take a different subsample for each one of these methods, each one of the decision trees. And then at the end, use this majority voting or averaging technique to make the prediction. So kind of the simple pseudocode is for one tree, you bootstrap sample, you construct the decision tree, and there's some cleverness to how to do that. It's not just any old if statement, it's the right if statement, and we'll talk about that. And then you will aggregate multiple decision trees combining their predictions with some kind of weighting or averaging technique, and then that leads to the final prediction. So just talked about this, bootstrapping, very simple. If you hear the word bootstrapping, it just means sampling. I've sampled it, and we're kind of making the assumption that there's a normal distribution in the data. Okay. You do with bootstrapping, you resample with replacement. So we're going to take a sample, put it back in the population, and then for the second decision tree, that sample may end up again in the next decision tree. Something to realize. All right. Tied back to the central limit theorem is that if you remember that we could start taking the mean of a distribution, and then we could plot the means of the means, and we would get a normal distribution. Okay. So that's kind of the connection between bootstrapping and CLT, is it really leverages the resample to approximate the sample distribution of the population. Okay. Some advantages, really, you don't have to really know anything about the population distribution. It can be fast because we're taking a subsample of the data. Okay. And there's kind of rules on how to select the number of trees called the N estimators in the code that we have. And so I have got some code. So let's take a look at the code, show you how it works. Let's see here. Okay. All right, so pretty straightforward. We've done this at least 50 times so far. We've loaded the MNIST data set. We've split it up into train and test data, and then here is the line of code that does the random forest. Just got to make sure you add in the module up above, and then the only parameter I have is this N estimator. I guess we could talk about the random state, but that just makes sure that every time you run this, you're using the same seed, and actually you get the same random data. So that's what that does. So you can make predictions, or the tests that you run will be similar, so you can compare them. This is the key parameter right here called N estimators, which is the number of trees. And there are some kind of rules around selecting the number of trees. Then we fit, then we predict, and you can see on the MNIST data set that we got 97% accuracy, right? With the neural nets, we were getting 98, 98.5, something like that. So it's pretty similar. And I haven't optimized this. I could have selected more, could have changed the number of trees. We'll talk about that. The other kind of nice thing about random forest is there's a feature built in called tell me the most important features. It's called feature importance. It's a property, and it's returned with the object classifier. And I can pass that to a heat map, and it tells me what is the most important feature? In our case, what is the most important pixel? Totally makes sense. There's a pixel in the center of the image of all the handwriting data. That's the most important pixel. All of the numbers use that pixel, or a lot of them do. Maybe, I guess the 8 buttons. I can kind of see an 8 in it. Right? That's kind of cool. So then we have some other pixels in here noted by yellow that are the most important features. So it gives you kind of a map of where are the most important features. That's neat as well. It totally makes sense that a feature up in the upper left corner has no value. There's no data, no information in that pixel.
So we'll put in test data that was shifted.
This particular application using a sequential neural net, and really what happened is took the first column, stacked the second column below it, and we made one column of 784. So it would not work as well. Might have some, you have to train with that data. Now, when we get to convolutional neural networks, they're scalable. So you won't have that problem in you have a small cat or a big cat, it will identify it. Small 8s, big 8, to a point. It actually has a limit on how much scale we have, right? So, good question, good question. Okay, cool. So, random forest, really kind of cool. Well, how do you pick these N estimators? Let's talk about that. Go back to my slides, if I can find them. Here they are. Okay, a couple of notes on that. I mean, just kind of like the hyperparameters and neural nets is, there's no clear-cut rule. It's kind of frustrating a little bit, right? There's no, it depends on the application and the data that you have in the data set, how many trees you need. Well, no. So you're supposed to iterate through them and pick one that gives the best accuracy or performs the best for your performance measure. Okay, so you might try values from 50 to 500, something like that. And that basically talks about the trees. How many trees are created? How many if statements? It's kind of like this huge if statement. If this pixel is on and this one is on and this one is on, that is an 8. If this pixel is on and this other one up here is on and this one down here is on, that's a 4, right? So that's conceptually the way I think about it. Okay. You can get some fantastic results. So here's the MNIST data again, and then we talked about this. It's one line of code basically to get the feature importance. All right, the final thing is like I want to talk about is like, how does it figure out which if statements? That's kind of the key to the whole thing. Is like if I just randomly made if statements, if this pixel is on, then I think it's a 7, da 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 da. I mean, that's kind of a random way to do it, right? So there is actually some intelligence to how to pick the if statements, and it's kind of cool, and that it is related to a Nobel Prize winner by the name of Shannon, who developed communications theory in the 30s, 40s, and 50s, how to communicate, transfer data over wires and wireless. And so this is a part of information theory. It's from Shannon's work. And let's see, I have some code to show off something called entropy. Okay, let me just kind of walk through this, and I have a simpler example, a better example, I think. Okay, so this idea of entropy is that if you have binary classification, I have a set of data, and it was a 50-50 distribution, 50%, 50% of the two classes. There's not very much information in that because I could just randomly select and it's 50-50, right? But if it was 90-10, there's actually information in the data set because it's primarily one of the classes. And you can measure that, you know, the probabilities beforehand, right? And we can do that. Like, how many 8s do I have in this class? It's 10% to start out with. well, let's say if it was, 8 or not an 8, that's a binary classification, that would be 10% and 90%. And so then we can test this, the probability after we do an if statement, a decision tree, and test this again. And if there's been information that's gained after the if statement, our probabilities of noting an 8 have improved, then there's actually been information gained in that if statement. So that's conceptually the idea of what's called entropy. So you measure the entropy, and entropy people think of like heat dissipation. A 50-50 distribution in a binary classification is it's random, right? You can just select something and get a random result. So that randomness, high randomness, is a high entropy. If I had 10-90 split, there's low entropy. It's all kind of around one solid number, 90% and 8. So that's conceptually the way to think about it. So I have this nice little code. Then I figured out a better way to show this. So I like this idea. So if I took the probability, or took 0, 0 here as my first example, and I calculated the entropy, and there's an equation for the entropy, and it's basically the log of the probability of this being a number minus the log of the probability that it's not. And you calculate that, and then you calculate that for that value that has the high probability, or the most important feature here, which is pixel 1314. They have two different entropies. So for example, data has a high entropy at 1, binary class of both being 0.5 probability, and a low entropy when one class is high probability, near 100%. And here's a plot of it, right? So both 50% probability, you have high entropy. If you have a low, for two classes, you have, let's say, 1 and 99%, then you have low entropy. And then if you have 99% and 1% for the other condition, you have low entropy here. So if you go from a high entropy to a low entropy and rate all of those pixels and pick the if statement, it gives you, it maximizes the information gain. Then that tells you the order of the if statements that you should take. So that's kind of conceptual. Yes.
So how do you calculate that change in entropy at that point? Learning like that you got information. Like if that's
Yeah, you compare the subset after the if statement. Just the probability after the if statement. Data set before probability, and then now you have done the if statement, and now what's the classification there, and
whether or not the probability.
if you think about it, it's like if I wanted to look at the weather, I had two variables. I want to look at the weather and the temperature. Is it cloudy, sunny, or second variable being temperature? Usually one of those variables is a better predictor than the other. That's kind of what this entropy is like. Well, which is the top variable that's the most predictive? Let's pick that one at the top of the tree. Then take the next set of data and figure out where the highest probability is for the next if statement. Maybe that's even a simple way to describe it. Like if it's raining outside, I know I'm not going, even no matter what the temperature is. So which variable has the highest amount of information that will lead to the best predictive model? And then you do that recursively through multiple layers of the decision. Right. It's easy to implement, but the accounting of all that is very rigorous, very detailed. Luckily, we've abstracted it to like a couple lines of code. I think you should know the concept of entropy and just conceptually what it is in information theory. It's basically part of a Nobel Prize, right? And communication theory. It applies in communication theory when I'm communicating data across on a wire or wireless, right? How much noise and how much information is in the data. Tell that about the distribution. Okay. So, wanted you guys to get a little background on that. But the key thing today actually was, let's open up your data set and let's talk about that for project one. So I loaded it into a spreadsheet. You know, I could put it into Pandas data frame and all that, but I kind of like looking at a spreadsheet. I can scroll around and look at it. So let's talk about this. Now, so here, there are 50 different features, input features. Okay, and then there is a website that I've given to you. That's not it. It's not Blue Baker. Let's see. This one. I don't remember where it is. This one. That's not it.
The one that was directed to the right of that, blank.
This one.